Welcome back to the course on drone systems and control. Lecture 3, we talk about rigid body and coordinate frames. What are the objectives of lecture 3? Lecture 3 we are going to talk about understanding of rigid body and coordinate systems. We will define what is rigid body. We will try to understand different coordinate systems of rigid bodies, differentiate between body fixed or world fixed inertial coordinate frames, and what is a coordinate transformation. How do we do from one frame to another frame, right. So, what is a rigid body? We are looking at object, so let us say n particles in a particular object forms a rigid body if the distance between any of the two particles is always fixed, constant. This will give the body, give a specific shape, size regardless of external force which is acting on it, right. So, example, your aircraft wing frame. In a multi-rotor we talk about the structure of the multi-rotor, your propeller, all this an example of typical rigid body. What are the properties that we are looking at? They have a definite mass, the total mass of the body. There is a center of mass, that is where average position of mass distribution being present. You have moment of inertia, which talks about resistance to rotational motions, and you talk about degree of freedom, right. It usually is 6 degree of freedom, 3 translational motion, 3 rotational motions, right. The motion of the body, as I mentioned earlier, it has two part, translation motion, right, movement of the entire body without a rotation, and rotational motion. This body rotates about its center of mass or any other fixed point, right. Now, look at the reference frame, right. So, we need a coordinate system to define the position of the drone or orientation and motion of this rigid body, right. So, coordinate systems are very, very important. In a drone, we use a different frames for different purposes, for a different frame when I say different coordinate systems for different purposes. For navigation purpose, control or defining the dynamics of it, we need different coordinate frames, right. So, what are the different type of reference frames we are talking of? Inertial frame or a world frame, right. It is a fixed frame that does not accelerate with drone, right, used for global positioning, or it is used for navigation, or used for mapping. If you are looking at a target from a specific drone, you can say I have seen this particular target in that location which remains constant, right. Body fixed frames or what we call local frame, right, moves along with the drone and is centered at its center of mass, right. X axis usually pointed forward, y axis is always sideways, z is downwards, what we call this as NED convention, right. Usually it is used for measuring the force, torque, control calculations, all that, or dynamics of this drone. If you want to define, we use the body frame, right. For UAVs, we talk about positioning of the drone, right. We wanted to position a drone in a world coordinate frame, where is it, right. We define it in the inertial frame. Usually IMUs measures in body frame. We need to transform inertial measurements into an inertial frame, right. The drone controllers compute what is the RPM required, right, what is the change in RPM that I need to have such that the particular drone move from point A to point B. That calculations are in body frame, right, where the motions are in inertial frame. So, you need to know how to convert them in a way so that you can compute change in position requirement into change in command which need to be given to the motor in a body frame. Okay. So, this is what I mean. The inertial frame is the fixed frame of reference, right, from which I am going to represent where this particular drone is, right. And the motions of this drone Basically, I'm talking about the dynamics of the drone, the rotations and translations I'm going to define with respect to body frame, and I will translate that to an inertial frame. Right? Now let's look at inertial frame in detail. Inertial frame, as I mentioned, it's a stationary global frame of reference which usually used to describe motion, right, and transformations. So it's a frame of reference assumed to be at rest or moving at a constant velocity, right. What we call this non-accelerating frame, right. It's considered as a non-accelerating frame, or it does not influence by rotational or gravitational effect. Of course, we make some approximations, right. So if you are talking about certain region, we have just defined the frame with respect to that, right. Or one can choose a star as a fixed frame of reference, and you can define the motion with respect to star, right. What is the characteristics we are looking at in the inertial frame? It's a stationary reference frame, right. Just to give you a recap, I am reiterating this. It does not move or rotate relative to the distance of the celestial body, right. Typically aligned with Earth or idealized global coordinate system. Global coordinates, what I mean global coordinate system, it generally used for a fixed frame of reference. It is used for trajectory planning, it is used for navigation from one point to another point. It is also to understand where the drone is at any given time and what orientation the drone is. It's what is the heading of the drone, in which direction it is moving. I need a global reference system for that, right. This inertial frame of reference is used for large scale navigation, what I mean long distance navigations we are talking about, right. We make certain assumptions for inertial frame of reference. Earth is often approximated as a stationary for a small applications. When I meant small, means small region where the drones are navigating. The gravitational forces are considered to be constant within the local region. So we are not looking at the variation of the gravitational force. If you consider that, then this is no longer inertial frame of reference. Right. Now we look at the conventions, axis conventions, right. What is the axis which we are talking about? X, y1, x inertial, y inertial, z inertial, right. X inertial is the direction pointing towards local east, right. It is defined as a global x axis. Y inertial is the direction pointing towards local north, that is a global y axis. Z inertial, Zi, right, it is the direction pointing downwards towards the earth center. We represent this as Z and U, right, or we can say it is an upward in an ED coordinate system, right. Common systems, when you are looking at east, north, up, ENU, or you can use north, east, down, right. NEDs are commonly used in aerospace or UAV control due to compatibility with respect to flight dynamics. We'll look into that when we go into 6 degree of freedom model definition in the subsequent lectures. So let's look at what is north, east, north, up, ENU frame, right. I am trying to define. Suppose I am on the surface of the earth, right. I am defining my fixed frame of reference, right. What is my x axis? X axis pointing towards the east, that is my xe, right. Y pointing towards the north, right, that is y inertial, and then you have your z inertial, right. Z inertial is pointing vertically upwards or perpendicular to the local surface. The surface is shown in the green color, right. So usually any point can be represented by latitude, longitude, right. The phi and lambda represent what latitude of the you are, or what is the longitude. I can position yourself in that particular plane, right. Now what is the characteristics of this northeast ENU frame? Earth fixed, but it is very local, right. The frame is attached to the specific point on the earth surface, what we are showing in the green color here. So, right, that is a local plane, right. It does not rotate with respect to UAV, but it is useful for navigation in a smaller region where I am assuming the curvature of the earth is negligible in that region, right. It is common in geospatial and robotic application space. We use this ENU frame. It is usually used for mapping, it is a local plane, right. We use the GPS data to interpret the position of the drone in this case, and we also use it for UAV navigation. And this END is often used in civil engineering too, when we talk about geographical information system, where I wanted to understand the map of that particular region. I am trying to look at the terrain variations in that smaller region. They use this ENU map, right. So what is the application? I use it for GPS based UAV navigation or geographic mapping or survey purposes. We use this ENU frame, right, or sensor based data fusion. If I wanted to do, I use ENU frame of references. Northeast down frame, NED coordinate system, right. Again, if I am trying to define what is my x, y, z, right, I am talking about geographical frame of reference centered at a chosen point on the surface of the earth. Again, I am trying to talk about a smaller region here, right. I am trying to define what is my x, right. Xn is, which is the north, right, that is my x, n, which is pointing towards the north, geographic north, yn pointing towards geographic east, your zn pointing towards downward direction, right. It is perpendicular to the local surface pointing towards the earth center. That is your NED coordinate frame of reference. Earth, this particular NED coordinate is also earth fixed, but it is local, right. Again, the frame moves with UAV, but remains aligned to the earth NED directions. It is suitable for short range navigations where earth curvature is negligible, right. Similar to ENU frame, we also ignore here the curvature aspect of it. It is commonly used in aerospace and UAV, again used for autopilots, for talking about point to point navigations, or we use it for positioning system, and we also use it for control systems where you wanted to track a specific trajectory, or you want to execute a mission to go from multiple points which is defined on this frame of reference, and UAV you have to go to all those points and return back, right. This particular coordinate system is preferred over ENU in aviation particularly due to its alignment with respect to aircraft conventions. Okay. What we talk about, altitude decreases in the downward directions, right. That is why we just use this frame of reference. Okay. Again, one can use ENU or NED. Its NED is preferred when you talk about position or navigations of either UAV. It is also used in flight control system, basically when we talk about point to point navigations, or we talk about stabilization, right. What is the attitude or what is the orientation it has to maintain with respect to the frame of references, right. Path planning, obstacle avoidance, on all these we use the NED frame of reference. Now comes to body frame, right, which is a local frame. Inertial frame is a global frame, body frame is the local frame of reference, right. This is a reference frame, is rigidly attached to the body itself, right, the UAV itself. Moves, rotates with respect to UAV, that is a very important aspect, right. It moves with respect to UAV. It is critical for describing the dynamics of the UAV, talk about the control inputs that you want to apply to achieve specific orientation and speed, right. All the measurements are done is relative to the vehicle orientation here, right. Typically centered at UAV center of mass, or what we call CG. It's another fixed point on the body where we define this coordinate system, right. All the forces generated by the UAV or force, torque, speed, I would put it not speed means as a magnitude aspect of it, right. Velocity, all defined with respect to this coordinate frame of reference, right. It is very physical to the body of the moving object. What are the characteristics of local frame of reference? It is relative to the UAV, right. It moves and rotates with respect to UAV, as I mentioned earlier. It used to describe the motion of the rigid body, orientation of the rigid body, the forces and rotational forces acting on this rigid body can be expressed in local coordinate system, right. Usually these axes are aligned. What I meant is it is aligned with respect to the physical structure, so that I can easy to define the orientation of the forces and moments that what we are getting on the body, right. Usually we use local frame of reference to define the 6 degree of freedom model or the dynamics of the vehicle. Here is a drone, we use the local frame of references. Okay. So let us talk about transformation from body frame to inertial frame or inertial frame to body frame. First we talk about inertial to body frame, right. What is that we need? We need to know the position and orientation, right. That is the first requirement. I need to know what is the position and orientation of this particular UAV. What I have to do? I have to convert from, right, inertial frame of reference is my position, right. It is all expressed in terms of global frame of reference, right, either in NED or in ENU frame. NED is most preferred, so herein we will use NED alone. I had to transfer the positions from NED frame to the moving frame, which is the body frame, right. So how am I going to do? I need to perform certain rotations, or I can perform the rotations either in Euler angle or in quaternion. We will talk about it in the next lecture, right. What are the angles that I am talking about rotation? Rotation about x axis, that is my roll. Rotation about the y axis is my pitch, and rotation about the z axis is my yaw, right. So I am going to talk about the transformation here from inertial to body frame. So I am defining the rotational the transformation matrix here. Here the C represent cosine, S represent sine. So for the simplicity I just put C theta and C psi, which means cosine theta and cosine psi, right. So I can just simply use this rotation matrix to transform information from inertial frame expressed in inertial frame to body frame, okay. Now body to inertial frame, right. Why do I need? I am talking about attitude of the aircraft, right, pitch, roll, yaw, which are all defined with respect to the body axis, but I wanted to take the attitude to the inertial frame of reference, okay. I need to convert the state of the UAV, right. What are the forces acting on the UAV? What is the velocity of the UAV, or how much acceleration I have on the body? All these are measured in the local coordinate frame of reference, that is a body frame of reference. I want to convert these information to inertial frame of reference, right, which is NED coordinate system. I am going to use the same rotation matrix here, what I call RIB. I am transforming from body coordinate to inertial coordinate here, right. So the transformation equation, if you look at anything I wanted to transform from body to inertial frame, V inertial is equal to RIB into VB. See here the subscript B represent the coordinate system, that what I am talking about, body coordinate system. Subscript I represents the inertial coordinate system. Okay. So, I can use this transformation matrix to transform any of the measurements that I have in the body coordinate to inertial coordinate frame of reference. In a summary, what this lecture talks about: what is rigid body, what are the different coordinate system we have, the global coordinate, local coordinate, that is what we meant. Global is inertial coordinate and local is your body coordinate reference, and how we transform information from one coordinate to another coordinate frame of references, why we need this coordinate frame of references, and so on. Okay. In the next class, we will discuss about rigid body transformations in particular. Thank you.